Tokyo researchers have just shattered scientific dogma. They created diamonds without heat, without crushing pressure, and without volcanic forces. Instead, they used a beam of electrons inside a microscope to build nanodiamonds atom by atom. For decades, experts believed electron beams could only destroy delicate molecules, but this experiment turned that belief upside down. The very tool once seen as destructive has now become a factory for the hardest material on earth. Diamonds are more than gemstones. They are symbols of extremes. Deep underground, carbon transforms only when it's crushed by pressures greater than a million atmospheres and heated to thousands of degrees. That's why natural diamonds take billions of years to form. Humans eventually learned to replicate the process using brute force, high pressure presses, and super hot plasma chambers. It worked, but at a cost: enormous power consumption, massive infrastructure, and diamonds that are often flawed or limited in scale. This has been the accepted wisdom for decades. To create diamond, you must fight against nature with overwhelming force. And yet, a small team at the University of Tokyo, led by Professor Eiichi Nakamura, has proven that belief wrong. They showed that diamonds can be born not from violence but from precision, not from crushing pressure but from the controlled touch of an electron beam. The secret lies in a molecule called adamantane. At first glance, it looks ordinary, but its structure is extraordinary. Its carbon atoms are arranged in the same tetrahedral pattern that defines diamond itself. Each carbon is capped with hydrogen, making it stable but also hiding its true potential. To turn adamantane into diamond, those hydrogens must be removed and the carbons must link together. Scientists knew this in theory, but no one could make it happen without high pressure. Until now, inside a transmission electron microscope, a machine usually used to observe atoms, not to create them, the team focused a beam of electrons onto adamantine crystals. Under normal circumstances, this should have destroyed the sample instantly, but instead, something remarkable happened. The hydrogen atoms began to detach, and the carbon atoms started forming new bonds. Slowly, the cage-like framework knitted itself into a diamond lattice. What should have been destruction became creation. The result is a flawless nanodiamonds, just a few nanometers across, each one no bigger than a virus particle, but each one a perfect crystal of diamond. And here's the part that stunned even veteran scientists. This process happened under modest conditions. No massive presses, no searing heat, just controlled electron irradiation at near room temperature. To put this in perspective, traditional synthetic methods like high pressure, high temperature presses consume megawatts of electricity. Chemical vapor deposition demands reactors hotter than the surface of a star. Both are expensive and complex. But here, diamonds grew in seconds inside a microscope chamber powered by a beam of electrons. The implications are enormous. For years, the electron beam was seen as an enemy of organic chemistry, a destructive force that tears delicate molecules apart. But this work shows the hidden truth. With the right molecular design, an electron beam can be transformed into a tool for constructive chemistry. It doesn't just reveal matter, it can build it, and the choice of adamantane was no accident. Other hydrocarbons failed completely, but adamantane's diamond-like skeleton made it uniquely suited as a precursor. This discovery suggests a new design principle for future experiments. Choose molecules that already carry the blueprint of the crystal you want, then let the electron beam finish the job. But this is not just a scientific curiosity. Nanodiamonds have properties that make them invaluable for the technologies of tomorrow. They can host what physicists call color centers, tiny defects in the crystal where electrons and photons interact in unique ways. These centers act as quantum bits, as sensors, and as communication nodes. In other words, they are building blocks for quantum computers, quantum networks, and quantum sensors capable of detecting signals as subtle as a magnetic field from a single neuron. The applications don't stop there. Nanodiamonds can be used in advanced imaging, in biomedicine, in surface engineering, even in space exploration. And here's the twist. This breakthrough also changes how we think about the cosmos. For decades, scientists have found nanodiamonds inside meteorites, puzzled by how they formed without Earth-like conditions. The prevailing theory was cosmic impacts and pressure waves, but now a new possibility emerges: cosmic rays, high energy particles flooding through space, may have acted like natural electron beams, sculpting diamonds out of carbon dust. This Tokyo experiment may have solved a riddle written in the stars. The challenges ahead are real. Right now, the method works at microscopic scales inside a TEM. Scaling up to industrial levels will require new electron beam tools, new ways to handle precursors, and new strategies to control size and purity. But the proof of concept is undeniable. For the first time, diamonds have been made not by crushing, not by burning, but by guiding atoms with beams of electrons. And later, when researchers refine this method, we may see electron microscopes evolve into something entirely new, not just instruments of observation, but instruments of creation, machines that can sculpt matter atom by atom, opening doors to materials we can only dream of today. The story of diamond has always been one of extremes, but now a quiet laboratory in Tokyo has rewritten the rules by showing that destruction can become creation, that beams can build instead of break, and that the hardest material on earth can be born without fire or pressure. They've changed not just how we make diamonds, but how we think about chemistry itself. Don't forget to like, subscribe, and comment your thoughts below, because the future of material science has just taken a dazzling new turn, and you'll want to stay tuned for what comes next on Dezhn.